Okay, in this video we're going to continue with section 2.5 and in this case we're going to talk about synthetic division and something called the remainder theorem. And so what I'm going to do is kind of build off of the last example from the previous video. And if you recall, in the previous video we divided x cubed minus 7x plus 2 by the binomial x minus 2 using long division, and the solution we got, or the quotient polynomial we got, was x squared plus 2x minus 3, and then it was plus the remainder, negative 4, over the divisor, x minus 2. Now there is a shortcut for this problem. We could have actually divided x minus 2 into that dividend x cubed minus 7x plus 2 in a shorter, faster way, and it's called using synthetic substitution. So we could have used synthetic substitution with the zero of the divisor. So what I mean by that, if you look at our divisor x minus 2, the 0 is just the value that makes that 0, which is just x equals 2. So what I'm saying is, if we were to use synthetic substitution with that 0 factor, right, we would actually get that same quotient polynomial. Let me show you how. If I use synthetic substitution, you'll recall you have to make sure you write down all of the coefficients of the polynomial in standard form with all terms included. So I have 1x cubed. Remember, there were 0x squared, so we have to use 0 as the placeholder. Negative 7 is the linear term, and then the constant is 2. So this is the setup for my synthetic substitution. I'm going to start by dropping down the 1, and I multiply 2 times 1 to get 2. If I add 0 and 2, I get 2. Now if I multiply 2 times 2, I get 4. Negative 7 plus 4 is negative 3. And when I multiply 2 and negative 3, I get negative 6. And when I add, I get negative 4. Now you might be thinking to yourself, well, that doesn't look like much of anything, but actually it is. If you consider this negative 4 right here, let me see if I can highlight it for you. This negative 4 pops up right here. That is our remainder. Now check out, the negative 3 also showed up in our problem. This negative 3 is right here. That's our constant. And the same with the 2 is our linear coefficient in our quotient polynomial. Why isn't it circling? And then I have 1 is the leading coefficient of the quotient polynomial. So the last number that you always get here will always be your remainder. And that's absolutely key. Once you have identified your remainder, the term right next to it, or the number right next to it, is your constant. And then this would be the x coefficient, and then the x squared coefficient. So the quick way of doing this would have just been to write, all right, I have 1x squared plus a 2x minus a 3, and then I can do plus the remainder, negative 4, over the divisor x minus 2. This process is actually called, instead of synthetic substitution, this is called synthetic division. And that's what we're going to focus on for the remainder of this video. So to kind of summarize this synthetic division, we used the remainder theorem. So this is the remainder theorem. And I'm kind of going to make the language a little bit easier to understand. If you are dividing a polynomial, let's call it any polynomial, f of x, by a binomial, and it's key that it's got to be of the form x minus k. So if we're dividing by just a linear binomial of this form, then the remainder the remainder is, it's a terrible S, it's hard to write with these things, is just f of k. That is your remainder. And so what this really means is, if the remainder is f of k, we just want to use synthetic division to do the division for us. So let's do a couple of examples of applying the remainder theorem. Let's call this example 1. I want to divide the polynomial f of x equals 2x cubed plus 1x squared minus 8x plus 5 by x plus 3. And I'm going to make sure I use synthetic division. Okay? So this is how we have to do it. The first thing that students might make mistakes on is this. When you look at your divisor, x plus 3, you have to make sure it's of the form x minus k. Now, you might be thinking, well, I'm not subtracting something from x, I'm adding. Well, you could think of it that way, or you can think of it as really the k value is just the 0 of that factor. So x plus 3 equals 0 when x is negative 3. So really, I'm subtracting a negative 3 from x, which makes it x plus 3. Or another thing students I know do with success is they just look at whatever number they see with the x and they take the opposite of that, and they know that's the number they synthetic divide with. So negative 3 is really what we're going to synthetic divide out from the polynomial to do the long division here, or to do the division problem. Now I just have to make sure I write down all of the coefficients of the polynomial. It's 2x cubed, 1x squared, negative 8x, and then a 5. There is no missing term, so I don't have to worry about putting a 0. And I drop down the 2, and then I multiply. Negative 3 times 2 is negative 6. If I add, I get negative 5. When I multiply, I get 15. When I add, I get 7. When I multiply that, I get negative 21. And when I add those, I get negative 16. Now, what that means is the negative 16 is my remainder. This is my constant. This would be the x coefficient, and this would be x squared. If there was another number out here, that would be my x cubed coefficient, but there is not a number there. So my solution is 2x squareds minus 5x plus a 7, and then I'm going to do plus the remainder over the divisor x plus 3. It's as simple as that. That's our solution here. Let's do another example. Where's the beginning of the page here? So example 2. Let's divide 3x cubed minus 4x squared minus 28x minus 16 by x plus 2. And again, what I want to do is, since I'm just dividing by an x plus 2, and this is a nice linear binomial, I'm going to use synthetic substitution, and my k value here is the opposite of positive 2. It's negative 2. So I'm going to synthetic divide out a negative 2, and I'm going to write down the coefficients 3, negative 4, negative 28, and a negative 16. There are no missing terms, and it's written in standard form kind of nicely for us. And when I do this, I drop down the 3, and I multiply, I get negative 6. When I add, I get negative 10. If I multiply negative 2 and negative 10, I get positive 20. When I add those, I get negative 8. 2 times negative 8 is 16, and when I add that, I get 0. Now, something interesting just happened. 0 is the remainder. So that means the quotient polynomial, this is just the constant term, this is the x, and this is the x squared. The result of this division problem is equal to 3x squared minus 10x minus 8. There is no remainder. So that means the x plus 2 divides perfectly into that polynomial. Now, what's more than that, guys, what I could do is I can rewrite, if you think of this big equation, right? If you take a look at that equation, I divided this polynomial by this dividend, and I got exactly that polynomial. I think you guys would agree if I were to multiply both sides of this equation by x plus 2, the divisor, and if I multiply this side then also by, I'm just going to write over here, x plus 2, these would cancel out, and that means the original polynomial 3x cubed minus 4x squared minus 28x minus 16 equals the product of 3x squared minus 10x minus 8 times x plus 2. And if you think about it, what we've just done is we've kind of factored the polynomial into the product of this times this. So this is actually leading into another huge theorem called the factor theorem. The factor theorem goes something like this. A polynomial f of x has a factor of x minus k if and only if f of k equals 0, i.e. the remainder, if I can spell that, it's always so hard to write with this thing, the remainder is 0. Basically what we're saying, guys, is if you ever do a division problem, a synthetic division problem, and you end up with a sweet 0 at the end, if you get a sweet 0, that means that what you divided by is a factor of the original. Let's show you how we're going to apply that in another example or two. So let's take a look at this one. Example, let's call this example 3. I want you to factor the polynomial f of x equals x cubed minus 6x squared plus 5x plus 12 given that x minus 4 is, oops, my pen just broke, is a factor. Maybe it's good my pen just broke. I might be able to write easier with my finger here. So this is what you're going to do, guys. In order to try to factor this polynomial, given that this guy is a factor, what we're going to do is divide that factor out and get a quotient that is the other factor of the polynomial. So to do that, I have to remember that the k value is the opposite of what I see with the x. In this case, that'd be a positive 4. So I'm going to synthetic divide out a positive 4, and the coefficients of the polynomial are 1, negative 6, 5, oops, that's a little close, 5, and 12. Now, I already know it's telling me that I should get it's telling me that this x minus 4 is a factor. That means I better end up with a 0 here. I already know that. If it's a factor, the remainder should be 0. So I kind of like these problems because you'll know that you're either doing it right or wrong based on the fact that you should be getting a 0 at the end of this synthetic division problem. Let's see if that happens. Let's drop down the 1, and when I multiply 4 and 1 I get 4, and when I add those I get negative 2. When I multiply 4 and negative 2 I get negative 8. When I add those I get negative 3, and when I multiply 4 and negative 3 I get negative 12, and when I add those I get my 0. So that is my remainder, and that should not be a surprise. I knew that x minus 4 was a factor. So my remaining quotient polynomial is 1x squared minus 2x minus 3. Now the problem here is I want to factor this all the way down. I know that right now if I had to, my polynomial f of x can be written as the product of this new quotient polynomial times my original x minus 4, right? But it's kind of factored, but we should try to see if we can factor that all the way down. And I think we can. We're going to have to employ some of the strategies we learned in Chapter 1. The leading coefficient's 1 here, so I could just try to find two numbers and multiply to -3 and add to -2, and that would be -3 and +1. So I can simply write x minus 3 times x plus 1, and then I'm going to drop down the original factor, x minus 4. Now my original polynomial is factored all the way down, and to even go further, if I had to, I could find all the zeros of this polynomial if it was just set to 0. I can set each factor equal to 0. But that's the idea. I'm going to do one more example with you. And it might help. Let's call this one example 3. And let's say it's given f of x equals 4x cubed minus 25x squared minus 154x plus 40. So given that polynomial and the fact that x equals 10 is a 0, we want to find all zeros. So this problem may look on the surface to be a lot different than the previous problem, but it's, in essence, it's asking for the same thing. When they tell me that x minus 10 is a 0, they're basically telling me that one of the factors of this polynomial is x minus that, x minus 10. Well, if I know that x minus 10 is a factor, I can synthetic divide out the 0, 10, from that polynomial and get the quotient, which I should be able to factor to find all the rest of the zeros. So let me show you what I would do. I would synthetic divide out the 10 from 4, -25, -154, and 40. Those are all terms are there. It's written in standard form. We drop down the 4 and we multiply to get 40. If you add those, you get 15. If we multiply 10 and 15, that's 150. If we add, that's -4, and when I multiply those, I get -40, and to no surprise, we get a 0 remainder, which it's telling me it's x equals 10 is a 0. So again, a nice way to check to make sure you didn't make a mistake along the way. You should get a 0 at the end here. Now, this is my quotient polynomial. I have 4x squareds plus 15x's minus 4. And now I'm going to try to find the zeros of that new polynomial. Now, ideally, we should be able to factor this. So I'm going to look for a GCF, and I wish I could divide out of 4, but I can't. So I have to use like the California method on this one. I have to find two numbers that are going to multiply to be -16 and add to 15. And luckily, that's not too hard. Two numbers that multiply to -16 add to 15 would be 16 and -1. So that means, so you remember the California method, what we want to do is take the 4x squared, your leading term, that's a terrible 2, the 4x squared, and we're going to divide that by 16 with an x, and then we're going to take the 4x squared and we're going to divide that with -1x. And I can go 4 goes into 16 4 times. The x's cancel. I have 1x on top. So one of the factors is x plus 4. And then here I can cancel one of these x's and I get 4x minus 1 for my other binomial. And now I just have to find the zeros for each. If I set x plus 4 equal to 0, I get a 0 of -4. And if I set this guy equal to 0 and add 1, I get 4x equals 1. And if I divide by 4, I get a 0 of 1/4. So these are the other zeros, and if I needed to include the first one, the first 0 that they gave me was 10. So I found all the zeros for that polynomial given one of the zeros. So the key is synthetic divide to save some time, and if you can do that and get a 0 remainder, you can factor that original polynomial and answer more questions. So thanks for watching. Let's get some practice in, and best of luck. Ask questions if you have them in class.